exponential probability density functions. So in methods, you are used to normal distribution for probability that looks like that. We've got a mean, standard deviation. This is a different type of probability function. So it's not a normal distribution. This is an exponential probability density function. So this is a specific case, an exponential case. And if I'm going to make it really obvious what case it is, it's a case where you're waiting for something to happen. So you might like to write that down, because that's pretty much the key. If you're thinking about exams, you'll see the word probability and you'll see they're waiting for something. So an example could be, and Joel Speranza, highly recommend his video, he uses shopkeepers waiting for someone to come to the shop. A really good example is a 1 in 100 year flood is like a really, really bad flood. And if you do hydraulic engineering, they talk about that a lot. The case of preparing your buildings, your culverts, those types of things for a 1 in 100 year flood. The thing that most adults think is once you've had that 100 year flood, there's not going to be another flood like that for another 100 years. So for example, in Brisbane, we had a really bad flood in 1974. We then had a really bad flood in 2011. Is that 100 years? No. This is memoryless. Floods don't go, oh, we've had our attempt now, we're going to just forget about it for another 100 years. Like, that's not how it works. So we're not doing normal distribution, exponential. So it looks like this. It starts off a really high probability, and then as time goes on, the probability goes down and down. So the main thing that this is affected by is this thing called lambda, which is a Greek symbol, looks like this. And it's all about the expected value. So the expected value for a 100-year flood is 1 in 100. Lambda is the inverse of the expected value. So it would be 100. So you flip the fraction to get lambda. The probability density function itself looks like this. So any time above 0, it's given by this function here. So these two are equal to this, and they have different lambda. So the area under the curve is equal to 1. So if we integrate this, 0 to infinity, we get 1. So yeah, let's just imagine we've got an average life of a motor, 1,000 hours. So that's the average. So lambda is 1 over 1,000. So how do I know that this is a probability exponential function? Because we're waiting for the motor to die, essentially. So the first one, it wants the probability between 800 and 1400. So the function itself is lambda, which is 1 over 1,000, e to the negative 1 over 1,000, t. So we're going to integrate to find the area under the curve between those two times. So if we integrate this, how do we integrate this? The coefficient in front of this t or x, whatever it is, you divide by that. So this divided by negative 1 over 1,000 is negative 1. So it's a definite integral. Alright, so we sub in this one, sub in that one, minus, so you're left with negative e, which is approximately 0.20. So what does that number tell us? If we look back at the question, So there's a 20% chance it'll die between those hours. So this time we're finding if it's more than 1200, so essentially just the same process. But this time we're going from 1200 to what? So what's going to happen when it gets to infinity? It's going to limit, and do you remember the graph? What happened to the probability when it got to, or got close to infinity? It got to 0. So this is going to become e to the negative infinity. Negative. Thank you, I forgot to put the negative out the front, plus e to the negative 1200 over 1000. So that becomes 0. And this we can simplify a little bit. 6 over 5. 30% chance it's going to last more than 1200 hours. Good old washing machine. Maybe it was made in the 70s, I don't know. But that's the type of sentence you would finish with.